there. So for you to follow along, if you have a CERN account, then use this link. If you don't, use this link. This is the binder for following a Jupyter presentation online. And this is using CERN's binder hub. We want to spread the load. So that's why there's 2 links. So only use this one if you have a CERN password, and if you don't, use this one. Okay, so once you do that, you will get to something like this. And if you've got this window open, you can just close it. And let's start into it. First of all, I'll second Eduardo's welcome message. Welcome to PyHEP 2020. And before starting the tutorial, actually before I started writing it, I looked at the survey to get a sense of who you are. I'd like to share a little bit about that. So this is the survey results. This is a pandas data frame. So we'll just look at some of the questions. We asked you what describes your occupation, and overwhelmingly, you are researching particle physics. We asked what stage of your career you're in, and most of you are graduate students doing research, quite a few postdocs, and then beyond that, professors, undergrads, early grad students, or researchers. We asked what languages you use, programming languages, and there were some, and what I'm doing here is I'm normalizing it because you could ask multiple, you could give multiple answers to this question. So if you answered like 6 different languages, we put 1/6 of a weight on each. And with that kind of weighting, yes, you're overwhelmingly C and C++ and Python. Given that this is a Python event, we know that you are interested in Python, but it's really interesting to see it's really half and half with the C++. Then we asked if you expect to use Python more, if you want to use Python more, and you were saying yes, which again, this is the place to do it. And then I asked a lot of questions about what packages you know about and you use, to get a sense of how much you already know about the Python ecosystem, so that I would know where to spend the introduction. Because a couple of years ago, I started each tutorial by asking for people to raise hands and say if they were familiar with NumPy, Matplotlib. A couple of years ago, the answers to these questions were usually no, but now it's overwhelmingly yes. Most of you use NumPy a lot. Matplotlib, SciPy, Jupyter, Pandas. You're familiar with these tools. So that's great because they're useful tools. Then, and some of these are less well known, but if you're interested, I included links to each of them so you can find out more about them. Then we asked the same questions about packages that are developed for particle physics. So the first 2 are fairly obvious. Your collaboration software framework, yeah, just about everybody uses that. Well, that makes an awful lot of sense. If your research group has custom software tools, many of you are using such tools. Root and PyRoot, yes, absolutely. But then other tools, Uproot, Condor, specifically I meant the Python interface, but I guess Condor in general. Root NumPy, Root Pandas, RootPy, iMinui. There's quite a bit less adoption of these particle physics tools than there is the general Python tools. So there's a lot to learn here. Then finally, what are your hopes and dreams for this meeting? Primarily, you want to learn about particle physics analysis tools, other than Root, but also Root. General purpose tools for data analysis, machine learning, and this is rather flat across the different things. So my takeaway from this is that you're mostly grad students and postdocs engaged in physics research. You use Python and C++ about equal. Major library of the Python world, so like NumPy, Matplotlib, machine learning tools. But you're less familiar with the Python library. Python library is intended for physics analysis, and you want to learn. So let's get started. All right. Since maybe about half of you know about Uproot. Uproot is a pure Python implementation of root.io. So as you have the root stack consists of root with PyRoot built on top of that and packaged with it. And then you can run analysis scripts directly on PyRoot or root. Root NumPy, which many of you have heard of, compiles into root, so it's also built on the root stack. And you can also use root pandas and build your analysis scripts there. But also, and I don't want to say alternatively, I want to say also, Uproot is a re-implementation of root.io so that it can be used independently. You can pip install Uproot. And so it can be easier to install in certain situations. It depends on awkward array, another thing I'll be talking about, which in turn depends on NumPy. And it has a loose dependence on a lot of other things. If you're opening root files that use LZ4 or Z standard, you'll need the library for that. But if you are not opening such files, then you don't need this. So the dependencies and the installation requirements for all of these things are just a bit looser. Awkward array is a generalization of NumPy to include data structures. So structured things like in these cartoons here, you have a certain data type that's consistent across these billion elements, but things can have different lengths, unlike normal arrays. And so these are interesting times, more ways than one. The ways we're in the middle of a transition from 3 to Uproot 4, and from awkward 0 to awkward 1, and these go together. So both of these tools have been out for a few years. They've had some physics analyses are based on them. And right now, this year, there's been a massive redevelopment of awkward array, basing it on C++ rather than NumPy, and a corresponding update of Uproot to use the new awkward array. So then that, and they are being introduced, they have different interfaces, but they are being introduced with new names so that you can import both. So both the old and new versions are independently installable and importable. Right now, if you want to use the old versions, it's Uproot and awkward. So pip install Uproot, pip install awkward, import Uproot, import awkward. And if you want to use the new versions, you include the version number. Later this year, there will be a transition. I'll be basically trying to very carefully switch the names so that awkward 1 and Uproot 4 will switch into the place of being just plain awkward and plain Uproot. And the current ones will go to Uproot 3 and awkward 0. So you can still do the Python trick of import Uproot 3 as Uproot, and your scripts will continue to work as they have been. And as you can see from this timeline, the old versions of these will be deprecated, but they won't be deleted. So if you have any analyses that depend on the old interfaces, they will continue to work. You'll just see that one line, import Uproot 3 as Uproot. Okay. Then that also begs the question of, in this tutorial, which versions should we use? And because they're ready for analysis use, we'll be using the new version. So everything I'll be talking about in this tutorial, we'll be using the new version of Uproot and the new version of awkward array. So let's get started. In a nutshell, Uproot provides a short path from root files to arrays. So you can do that. And Now from this root file, this TTree, this branch, has just been cast as a NumPy array, and there it is. So, but in general, we want to take more steps than that because you might not know where in a file something is. So let's break it down. Let's start exploring this file. The first step is you open a file, uproot.open, and give it a file name. If you're following Python best practices, open, I'm just going to do that. You can write things like this, and that will close the file after you exit the with block. But if you're doing things quickly on the command line or in a notebook like I am here, you can just assign it and let it not close itself when you're done. So then this file, or rather more precisely, this directory object, acts like a dict in Python, where you can say root.keys, and you can see all of the objects within it. So this has a TTree named events, and you can get that using square brackets. So there's my TTree. Now you see in the key name, there was this the semicolon 1. That's a root cycle number because root can have multiple objects with the same name in the same directory. But you don't need to use the cycle number when you're extracting things. We will take the latest one. And then if you're familiar with Python's mapping protocol, this is part of the built-in standard library. This root object is a mapping, so you can use it anywhere that a mapping can be used. So you can also get listings by type. So root.class names, here's a dictionary, and you can see that it's a TTree before you open it. This file is a bit more interesting. Nested directories has some nested directories. You can see that the keys have slashes in them, so you can navigate to sub-objects. And let me type something. Nested ders. You can say 1, and that's the subdirectory. You can say 2, that's the sub-subdirectory. 1, 2 tree is the TTree object. But you don't need to make them separate. You can use slashes. What you're doing here. Here the class names is more interesting. You can see that some of these are directories, others of these are trees. And all of the keys, class names, type names, values, iter, in Uproot have filters. So you can filter by class name is tree, just the TTrees, or you can get all the class names where you filter the name to include the letter T, whatever it is you want to do. So now that we can navigate files, one of the most useful objects in a file are histograms. So let's look at this file. It has a few histograms in it, th1f, th2f, tprofile. Now, histograms, Uproot is purely an IO library, so it really doesn't have all the tools for dealing with histograms, filling them, plotting them, etc. And the more Pythonic way of doing this is having a lot of different tools, different packages, where each package focuses on something. So actually, when we first get the histogram object, there it is, a th1f. The first thing we're going to do almost always is convert it into some other form for some other library to NumPy and get a NumPy style histogram, to hist, which I'll be showing later, to boost, which I'll be showing first. So this is a boost histogram. It belongs to the boost histogram library. If we didn't have boost installed, there would be an error message telling us how to install it. It's a clean design of n-dimensional histograms using the boost C++ libraries with Python bindings. And its focus is on just filling and manipulating histograms, so not even plotting. So if we want to plot it, there's another package for that. It's called mplhep. And so we can import matplotlib and mplhep, which is this connection between matplotlib and high energy physics, and just take that histogram, pass it to mplhep.histplot, a nice looking HEP style histogram plot there. And one of mplhep's features is that it knows about some of the major collaborations. Currently it knows about CMS and Atlas, but that's the sort of thing that can be added to. And so you can get things in CMS style or in Atlas style and get your plots approved by the plot committee. And then also two-dimensional. Okay, so that's nice, but there are all these different libraries to juggle. Oh, I don't want to install both Boost and also mplhep. There's a new package called hist with a deliberately short name. The intention's that you can just pip install hist and then get everything that you need in order to do the analysis. So with a hist, which currently you have to install like this because only an alpha version's been released, you say to hist, and then it just has methods like plot. You don't have to pass it to something else. And here's a 2D. And then it's got some nice high-level plots like plot 2D full, so that you get a nice two-dimensional plot, and also it's one-dimensional projections. And could one of the co-hosts mute all, please? There's somebody in the background there. It's also got nice plots like fitting and plotting in a single step. So am I unmuted? Okay. So, we'll be hearing more about these histogramming libraries later. And now I'll talk about TTrees. For the TTrees, let's start with this this diagram for nomenclature so that we're all using the same words. Inside of a T file, the main thing that you're actually working with is T directories, and directories can have subdirectories. And these can have histograms like the ones that we've just seen. A T-tree is one of the things that can live in a T directory. And a T-tree is a collection of branches all with the same number of entries. Generally, one branch is one array. That's the uproot way of looking at a tree. The actual data are stored in T baskets, so you'll sometimes hear us talking about T baskets. Maybe your basket sizes are too small, and so that's why your reading is inefficient. But if there aren't any problems, baskets are usually lower level than you care about. So, so really the way to be thinking about this is you have a T tree, and that has a collection of equal length T branches. Some of these T branches don't have any data. This is a question I sometimes get. Why does this T branch not have any data? Often it's because it has sub branches that do have data. It represents an object that has been split, and I'll be talking about splitting more later. Okay, so generally the first thing that you want to do when you open a T tree, like these events here, is show. So show will give you useful information about any objects that have a show method defined. So here you can see the list of all of the subdirectories, sorry, the sub-branches, sub-branches. Their C++ type names and their interpretation. Interpretation is an uproot specific thing. It's how we are translating the C++ data into an array, either a NumPy array or an awkward array. Some of these are as D-type, meaning this is going to be a NumPy array with a certain NumPy D-type. And some of these are as jagged. Only awkward arrays represent jagged arrays in an efficient way. I'll show that in a moment. So these T-trees, they also have a dict-like interface. So you can look at the keys directly. So this is how you can programmatically get that information. Okay, we have to mute everybody again. Can someone? All right. So just like a dict, you have keys, you have items for the key value pairs, and in this case, the values are branches. And type names to get those C++ type names that can be useful for filtering. This TTree is also a mapping. You can use it anywhere a mapping can be used. And these keys and values and items, they all have filters. So you can filter by, like, let's say your ntuple has a naming convention. You can select branches by a pattern on the name. You can select them by type. And you can also filter branch. And actually, any of these filters can take either a string or pattern or regular expression or a whole function, a function that returns true and false to pick out some of the branches. All right, so now we're getting to the thing that Uproot is really for, which is turning branches into arrays. So once you have accessed a branch object, there's that branch, you can just say .array, and it will turn into an array. Is there a loud background sound? People give me a...
No, it's fine, Jim. Can hear you very well. Now you're muted, Jim.
Okay, I'm back.
Okay.
Right. So this this thing that we got back in Uproot 4, the default is for every array to come back as an awkward array. So that's what that looks like. You can tell because it has a capital A. Let's take the first 20 of these and say .toList. And you can see that they don't have the same number of entries in each element. This is what we often call a jagged array, because if we look at this as a two-dimensional thing, the right edge is jagged. Some are short, some are long. And this was the primary motivation, the reason that we have this awkward array library that I'll be talking about more. So one of the, in Uproot 3, whether you get a NumPy array back or an awkward array back depends on whether the data are jagged or not. In Uproot 4, you can just specify it. So if you really want this to be a NumPy array, you say library is NP or write out the word NumPy. This is the standard abbreviation for NumPy. And again, looking at the first 20 elements, if we're going to make a jagged array in NumPy, it has to be an array containing array elements. So this is NumPy with data type or dtype object, because it's a NumPy array that has Python objects in it. Those Python objects are arrays. This is what you'll get if you're using root NumPy. So if you're familiar with that, then this is the way to get that. But generally speaking, this is less efficient, because really what you have is, if you've got a million events, this is going to give you a million Python objects, a million little NumPy arrays, and they are very little. It's like 2 elements in each. So the default will be everything comes back as awkward arrays, but you can override this by setting the library. So the difference between these objects, more than just the efficiency, is that awkward arrays interpret the nested list as a second dimension, and NumPy object arrays do not. So let's get an awkward array and a NumPy array. In the awkward array, we can say things like get the first 20 events, the 0th element from each of those as like a 2. I'm back. two-dimensional slice. And that's no problem. So for the first 20, we get the 0th. And now this is no longer jagged because we're picking the first element out of each. Then we try to do that with a NumPy array, and it just can't do it because in NumPy, each of these is a separate object. NumPy doesn't know that you can that this kind of multidimensional slice would be allowed because they're Python objects. Another valid library that you can use is Pandas. And Pandas has its own way of representing variable length structures. It's called multi-index. It's worth learning about. And so with a multi-index, you can say that each of these elements here has both an entry and a sub-entry. And that's a different way of representing this jaggedness. Now in that first one-liner that we used, we can now explain what it's doing. We used a colon to separate the file name from the file path from the object path. And that gives us this branch. And then if we wrap that as with np.array, this casts as a NumPy array. And so that is calling library equals np. And anything that tries to cast what you have as a NumPy array will use that method. So for instance, you can pass just this uproot open file name branch path. You can pass that right into matplotlib and it will plot it because matplotlib casts whatever it's looking at as a NumPy array. Warning, only do this with non-jagged arrays. If matplotlib gets a NumPy array of NumPy arrays, it will churn for a very long time before having some sort of error. Okay, so I have shown the array method. There is a similar method called arrays. So the pluralization is important. So whereas the array method will give you one array, the arrays method will give you multiple arrays. This exists in both Uproot 3 and 4. If they're NumPy arrays, that means that you get a dict of arrays. So here's the branch name and the array, branch name and the array. If they're awkward, the container is an awkward record. So as far as awkward is concerned, you have 1 million record structures where the elements of the record are, they're like structs in C. And for pandas, the array method singular gives you a pandas series. The arrays method plural gives you a data frame. So pandas makes this distinction between a single array and multiple arrays by series versus data frame. So all of these are packages of arrays that you might want to use in your analysis. Generally, with an analysis, you're going to be using more than just one branch, more than just one array. And actually, you could say that that TTree is Root's package of arrays. So for each one of these, you get them in a dict-like way, and because this NumPy one is actually a dict. And for awkward array and pandas, you can also use the dot notation. So you can put the name in quoted string if you have to. You can use a dot if this is a valid identifier for both awkward and pandas. Here above, we use the filter name to select branches. We can also select specific branches. Actually, let me scroll up to where we selected this. So tree, arrays, filter name, and I gave it a pattern. With the arrays plural method, You can give it a list of explicit ones. And there we've got just those three, PVX, PVY, PVZ. And you can do calculations. We can put a formula in here, or we could put an alias to formulas that are defined here. And the word alias is deliberate because this will also pick up on any TTree aliases that have been defined for your TTree. And you can also use them to do cuts. There isn't any performance advantage or anything like that to doing your mathematical calculation inside the string when you're fetching the array versus getting the arrays out and then doing all of your calculations on the arrays. You could have done this just as easily on the arrays when you get them out. Primarily, this feature exists to support TTree aliases. So multiple files. Typically, you'll have a lot of files with similar contents. The simplest way to deal with that is to just concatenate them all. This means reading them entirely into memory and making one array of all those files. If you have enough memory, go for it. You might not have enough memory. So this concatenate method is eager. It reads the whole thing right away and makes one big array of everything. And now that this is in memory, you can ask for particular fields. Alternatively, if you don't have enough memory, you can make lazy arrays. The interface for this is very similar, but it's called lazy. So here we say load it, and what this will do is it'll open the TTree metadata for all those files. So you still have to be able to open all of the files, but it doesn't read all of the data until you actually need it. And then valid question is, if this is not in memory, how can I see the values? Because we're looking at it, we're seeing some values from this thing. And actually, just the parts of the file, the branches and batches of events that are visible in this printout are actually read. So in this case, the N branch, the B branch, and the STR branch, the first files from these and the last file from this are read in order to show us that. So always these things are reading just enough to show us what we asked for. So if we say .af8, now the beginning and end of this have been read, just to show it to us on the screen. If we do a mathematical operation on it, then that will read the whole thing in order to do the mathematical operation. So after part of this lazy array has been read, you might be wondering, how long does it stay in memory? We want to be able to control that. We don't, for instance, want this to be constantly reread every time we do a calculation, because sometimes people think that lazy means it's going to be efficient, but actually the opposite of that can be true. You can sometimes have lazy objects be less efficient because you end up reading the same thing over and over again. So we want to try to control that. We can do that by passing a cache. You can make a cache, specify its size, and pass it in when we're opening the lazy array. And also, by the way, you can pass in caches to any kind of, when getting any arrays. By default, we're always using a 100 megabyte cache. 100 megabytes is not very large. So here we've passed it in. We look at the cache and it's empty. We look at this object and now the cache is not empty. It's loaded the first little bit and last bit of that. Really, it's just about 1,000 bytes, so not very much has been read. We do this calculation that runs over all the data. And now the cache has a lot more in it. And we can clear that, and it's empty again. So by keeping a handle on this cache object before you create the laser array or any other kind of array, can give you more control over the memory usage. But still, that control is implicit. The most control you can get over something is by explicitly iterating over it. And actually, when people are having memory problems, this is what I recommend. Because just loading the thing as a lazy array, that's fine. But but the reason that we load these things is usually to do calculations. And in doing calculations, that usually means that we're going to want to look at a batch at a time, do some computation on that batch, get rid of the old batch, and load a new batch. That's exactly what iterate does. So it gives us a for loop, but this is not a for loop over events. This is a for loop over arrays, and each of those arrays represents a batch. And here we are specifying what we want to read in, because it will read in everything that if we don't specify, it'll read in the whole TTrees in each batch. So this gives you complete control. And in each step of this loop, you get a batch of arrays, and you can do your calculation in the batch. If you're using boost histogram or hist, you can fill your histograms in this loop, one batch at a time. Okay. So now everything so far that I've been talking about have been numbers and jagged arrays of numbers. It is possible to read some complex types. So here's a TTree that contains a bunch of STL containers, vector of numbers, a vector strings, a vector of vectors, a vector of vectors, map of vectors, all the different things to make sure that we could read all of these different types. You can have vectors of structs, where the user-defined struct, if it's some sort of event object or particle object. And so any one of these, if you read them, you'll see that you've got some STL map of whatever this is. This includes, T-Lorentz vectors. T-Lorentz vectors is actually the most asked for type of object. So here, let's look at a bunch of them. Oh yeah, I'll load these T-Lorentz vectors into pandas. And then, because a T-Lorentz vector consists of a T vector 3 of momentum with X, Y, and Z coordinates and scalar energy, that's how it unpacks into pandas. It follows the root record structure, whatever it is, even if it's a user-defined object, and it'll break that into columns. And in this case, hierarchical columns, because these are, it's a T vector 3 nested inside of a T-Lorentz vector. And then there's a hierarchical index because it happens to be a standard vector of them. So sometimes there are errors that look like you've been able to read this type and that type, but then you try to read some other type and it doesn't work. Often I'll get these questions: why can't Uproot read this certain type of object? In some cases, it's because that object hasn't been implemented yet. In some cases, it's a bug with reading that type of object. But also in a lot of cases, it's a bug with something unrelated to that type. This was confusing in Uproot 3 because it didn't clearly distinguish the error messages between a deserialization error, like we're having trouble with this type, and other types of errors. So deserialization errors have been made a lot more explicit. And now, just so that you know what it looks like, if you're ever working with stuff and you encounter this, this is what a deserialization error looks like. If there's something you can't read, last Thursday, we found out there was a problem with t-hash list. This is what it looks like. It shows you that it's trying to open this object. It's trying to open this object within it. And you can see some of these numbers are looking okay. And then it goes all crazy. Oh, sorry. Double clicked. I should never double click in Jupyter. It goes all crazy when it gets to the size. And then it's trying to read bytes that are way off the end of the file because it was a deserialization error. It thought the size of this object was humongous. And so if you see that, this is what you should report. If you see a different error, then we want to see that too, but it's probably not a deserialization error. Okay, so still actually on this topic of data types, you may be working with files that have complex types in them, and you're given the option when you're writing it, if you have control over the process that writes this root file, to split or not split the file. The bottom line of this will be choose splitting. If at all possible to split, do so. So here's the same object in two files. The first has not been split. And here's what it looks like in TTree show. It says the event type is, the C++ type name for this is event, and it's interpreted as a bunch of objects with the model as a Python class of this event. And then the same thing in a split file looks like this. It's a branch with sub-branches for each field within that event class. And each of them has a different, very easily readable type. Numbers and strings and arrays of numbers. So it's the same data, and they look the same in root. So if you're in C++, you're going to get C++ objects for each one of these. But they look different in Uproot, because Uproot has this view of the world in which each branch is an array. So if there are any types in an unsplit object that Uproot can't deserialize, because we just don't know how yet, or there's a bug or whatever, then Uproot won't be able to read any of its data because it's all or nothing. If there are any types in a split object that Uproot can't deserialize, Uproot will be able to read everything else. Also, split objects are usually faster to read, even if you do read everything. So split your data whenever possible, if you have that choice. Here I wanted to say last word about Uproot. It is possible to write to root files in Uproot 3, not 4 yet, so I'm not going to be showing anything on writing files here. But just to set expectations so that you know, Uproot is never going to be a great way to write root files. Writing root files, it'll always be minimal. It'll always just be histograms and only basic types and TTrees. So numbers and jagged arrays of numbers. You won't be able to update an existing files, only making new ones. And it won't be as fast as writing with root. So writing of root files will be provided as a convenience. It already exists as a convenience in Uproot 3, but in Uproot 4 will be provided as a convenience. Just so that you know, it's a much more difficult programming problem. And if you want to write complex objects, or if you want to write a lot of data and therefore do it quickly, you should use root. Of course, you know, that's an open invitation to anybody, any programmers out there who are willing to try to do that in Python. Okay, so at this point in the talk, I will be switching over to awkward array. If you want more detail on awkward array, there's a whole talk on just awkward array here. And actually, this presentation was written for non-physicists, so so it gives some examples that are very generic, not physics specific. But okay, so this talk got way too meta. Okay, I should be not watching the chat while speaking, or I'll get confused. So yes, we're way meta. We're looking at myself, watching myself. Okay, so let's look at this mu1 data again. So here we have some arrays that could very well be NumPy arrays because they're flat, and other arrays that really ought to be awkward arrays because they are jagged. And yeah, we've already seen it's awkward to deal with jagged arrays in NumPy. The first time that we read them in without zipping them, but now I'm going to so-called zip them, which will make this whole file appear to be 1 million event records. So now the data type encapsulates the structure of these events. And by the way, in all of these, I'm implicitly import awkward1 as awk. Awk is the 2-letter combination. So you can see the data type of your data, and this can help you find out what fields have been read. So this here is just an expansion of that, where we didn't have enough room to look at it all. You can see that these objects have run number, luminosity number, event number, and then within that somewhere here, mu1 is var times all these things. So it's inside of these records, there are jagged arrays of these records. So the 1 million times means that there's exactly 1 million events. The mu1 var times means that the contents of the mu1 field are jagged. So we can look at a few of these. We'll just pick out the first 3 of them and say .toList, which will turn them into Python objects, which is generally a good way to use just a small set of examples so that you can get a sense of what's there. And you can see that these look like Python dicts containing fields that are numbers, and then this mu1 field is a list, the jagged array, of dicts. These are the mu1 records. This is kind of a natural way to think about this physics data. Of course, if they were actually Python objects, your analysis would be too slow. So, so we just view them with the 2 lists to get a sense of what's there. The data are not actually arranged as objects in memory. So each one of these fields, like the PT, the eta, and the phi, is each an array by itself. So actually, when we zipped these things together, we didn't actually change their structure very much. We're just viewing them in a different way. So structure changing things like pulling out all the kinematics fields or pulling out some other kind of field or zipping it in some different way, these are not expensive computations. You can dramatically reshape the structure of your arrays in using operations that where the performance, the time it takes, does not scale with the size of the data set. So you can project things out or remix them without any penalty. So if we just want to, from these events, pick the muons and then only these fields, we can do that. So now we've pulled that out. And now if I look at the type is 1 million times var, because we've already picked the muons, we're only looking at muons, times this kind of record. These are new records, but they were created instantaneously. We can assign to this. So we can say events of muons pz, and here you have to use strings and square brackets. We can assign that and do a calculation like take the events pt times the sinh of the, events muon pt times the sinh of events muon eta, and that's pz. So we can do that calculation. And now these objects have a pz field. And we can look at it, use the dot notation and all that. So this is a projection. We're projecting out a thing, and this here we've assigned a new column. This took order size of the data set to compute, but attaching it was free. Since all of you are familiar with NumPy, which we learned from those surveys, slicing with arrays and Boolean arrays is probably familiar to you. So what's new is that the Boolean arrays can now be jagged to slice jagged arrays. In other words, cutting particles. So we hear events.muon pt greater than 20. We get an array of Booleans, but they are jagged Booleans. You can see that that's a list of lists. You can see it's 1,000,000 times var times bool. And we can put that jagged Boolean array inside of square brackets to cut the muons. If you want to cut events, then you need to turn the jagged array of Booleans into a one-dimensional array of Booleans so that it applies to the events at the outer level. And you can do this with a reducer. Reducers are things like sum or max, but for Booleans, the most use for any and all. So you want to ask a question like, events muon pt greater than 20. You want to say, where is there any like that at the first axis, meaning reducing over the particles. So we want to get one per event. So true, the first event had such a thing. False, the second event did not, etc. And that is a flat Boolean array. And you can just pass that in. And now we're cutting events.
Jim?
Yes.
So just say that you've got 10 minutes for questions, including the questions, right? In your slot. Thanks.
Yeah, I knew I had 10 minutes left. And okay, so it's 10 minutes for questions. Right, so yeah, I'll figure this out. I'll be wrapping up. You can see the scroll bar here is near the bottom.
Yeah,
okay.
There's more for information. I think we're fine.
Yep, okay, great. So we can do a whole analysis this way. Awkward array has some new functions that don't exist in NumPy, such as finding the number of muons. That's something you don't need in NumPy because the answer would always be the same. But here it can be different, 2, 1, 2, 2, 4. And using things like this can sometimes be necessary because if you say, slice all events, taking the first muon from each, that's going to fail if any of the events have 0 muons. So then you'd want to use things like this num to select the events that actually have a muon, and then you can take its the first muon. Masking versus cutting. I think I'm going to skip over that in the interest of time, but we introduce a new thing called masking to put in nones instead of removing things so that your array doesn't change size and you continue using the same cuts. Sometimes you want to turn your jagged arrays into regular arrays for passing into something with machine learning. You need something with rectilinear dimensions. Look up pad none and fill none and flatten for how to do that. Flattening, you generally always want to flatten if you're ever going to plot something, because you can't plot a jagged array. There's combinatorics, like taking Cartesian products and then choose K. You need these if you're going to compute things like all pairs of muons in order to make a z-peak. So you want to find all of the the different pairs of muons without duplicating any. This combinations will let you get those pairs, and then you can do calculations on them like an invariant mass and compute masses. Now, the one thing I wanted to get to before we leave is that I saw from the survey that not all of you are familiar, well, actually, very few of you are familiar with Numba. This is not a HEP specific thing. This is general in the ecosystem. I think this is something that we should all be aware of. Numba compiles Python code. And you can use Numba with awkward, that's what I'll be showing here. But really, in general, I want you to know about this just in general. Import Numba as NB. And now any Python function that you write in which the types can be determined, you put numba.jit before it, and it will compile that Python code, just as though it were C code. And here I'm passing this events awkward array into it. So here we pass the events awkward array in so that we loop over the awkward array in a rather natural syntax, event.muon, muon pt, and have it just return a muon. So we're returning an awkward object, this record. But here, this is showing how you can write ordinary for loop code if your problem is complex enough that it's difficult to piece it together with Cartesian product or choose combinations. So that actually was my last topic. Few other examples with Numba. I really want to stress the point that Numba is a great thing to use. If you've calculated an invariant mass before, this would look familiar to you. You do for loops. If you want to do for loops to make your plots, you can do so with Python code in Numba and not lose any performance in doing so. So that's it. So now I guess I have 2 minutes for questions. I will open the floor. Okay, so is someone watching
Ashraf.
Yeah, thank you. Ashraf, question?
Yeah, in fact, I have a question regarding to the histogram filling and writing in Uproot. Is there a standard method for error handling, or do I have to handle the error myself?
What kind of errors?
I mean, the statistical error, for example, when I'm filling a histogram, root is handling the statistical error for me.
Right. Yes. So from Uproot side, it passes through the root errors, the sumw2, into the boost or hist.
Yeah.
NumPy histograms do not have errors, but then anything more about histogram objects, I'll defer to the histogram talks. Actually, we said, I'm just realizing that we said that we're going to take questions from Slido, and there are a lot of them there. So I will start with the most upvoted questions. The first question is, what are the main benefits of Uproot over PyRoot? Okay, so the trade-offs are these. In PyRoot, 100% of root is covered. Everything that you can do in root, you can do in PyRoot, and you can do it from Python. The downside is that can be slow, especially if you're doing it in a loop. If you're looping over 1 million or 1 billion events, doing that with a for loop using PyRoot, it's doing the full generality of turning your Python code into C++ in that loop. And I think if you just try it. If you're working on a small enough problem, then maybe it doesn't matter. But if you're working on a large problem, you'll find that it will just take a very long time to complete under PyRoot. There are good reasons for it. I mean, because of its generality, it's slow. Second question is, does opening a file with uproot4.open read the whole content in the memory directly, or does this only happen when specifying trees and branches? It only happens when specifying trees and branches. So in all of the examples where, actually, I'll use my diagram. Here's my diagram. Okay. When you first open a file, can you see my mouse, by the way? Because I'm moving my mouse over this first directory.
Yes.
Okay, good. When you first open a file, it just opens the T directory. Then when you say file square brackets my TTree, then it opens this TTree metadata, meaning not your millions of events, just the types of all the branches, the number of events, so just the TTree metadata. Then if you say TTree get some branch, then it doesn't open anything because the branch has already been read. Then you say branch.array, then it reads the array at that point. So the array method, the arrays method, the concatenate function, all of these immediately open. The lazy does not immediately open. It opens as soon as you use it. And the iterate method opens little pieces bit by bit through all the files. Why don't we get rid of root files together and switch to HDF5? Actually, we would not be able to do jagged arrays if we switch to HDF5. And in a lot of analyses, jagged arrays have been important. You could also ask root versus Parquet, and that's more similar because Parquet has hierarchical nesting like root does. But really, exabyte of data in root format. Root is a fine file format. So we work with what we have, and it's fine. When looking at T-trees and Uproot, you said that a T-tree is also a mapping. What does a mapping mean? Is that just a dict? A dict is a specific kind of mapping. It's the Python built-in general purpose hash map. Mapping is an abstract mapping. Mapping is an abstract dict. It means it has all of the methods that a dict has. It can do all the things that a dict can do, but it isn't necessarily a literal dict. If these were literal dicts, then everything would have to be read ahead, then all of the data would be read as soon as you've created the dict. Uproot, which parts of root are I/O? Just T-file or canvases and such? Which parts of root are I/O? By I/O, I mean T-file, T-directory, T-tree. That's basically what we mean by input-output. Is the cache safe for multi-threading, multiprocessing is this cache safe for multiprocessing? So multiprocessing will be cache safe because multiprocessing does not share data across the Python processes. So that's always safe. It uses a bit more memory though. Multi-threading, if you have your multi-threading, the preferred way to do this is to open separate objects in each of the threads. I guess maybe the best way to answer that is no. Don't open a single object in all of your threads unless you're only reading. And actually, most of these objects are read-only anyway, so no. We're now 5 minutes over. I don't know if Eduardo is going to call time, but if not, then I'm going to keep answering questions. Does Uproot 4 have...
No, sorry, Jim. Yeah, I think we should go with one, because after the break, we're still going to have 1.5 hours. So we should probably give some time for people to have a break, yeah.
Okay. Right, so there is a break now. Let me get back to this. there is a break right now. You are free to go to the break. 9:40 is when we start up again. So would it be all right if I stay here and answer questions during the break? Pressure on people to see even if they want to take a break.
I think anybody is free, right? That looks fine. If they want to continue discussing, they do, and if they want to get a coffee or tea, they go.
All right. Yes. So
get back nominally in 25 minutes. Say, okay, at 22.
Okay.
Bye bye. See you later.
Super quickly, Jim, are you able to answer the answer from the questions yourself?
Okay, I really can't hear you very well at all. You have to speak up.
Are you able to hit the answer button? And you can't see that, right? You don't have an answer button. I see it. Okay.
Yeah, I logged in as an ordinary user, I guess. Yeah, I'll have to log in as a special user to do the answers. Yeah, but I'll do that. I'll do that also, like offline. Yeah. Does Uproot 4 have all the features that Uproot 3 has? No. For instance, it doesn't have writing. I think that's it at the moment. Can you say a little more about reading weird objects in Uproot, particularly what custom objects work out of the box, what needs massaging, what doesn't work? That is a difficult question to answer because we discover what can't be read by encountering it. So the way that we find out about types of objects that can't be read is usually through GitHub issues. From all the experience that we have with Uproot so far, I have a very large collection of files that people have sent with this doesn't work, that doesn't work, this other thing doesn't work, and they weren't all type errors reading particular types, but many of them were, and so naturally I started with that to make sure that we can read most of those issues. But the best advice is to just try to read it, and if it doesn't work, then send a GitHub issue, and we'll see if we can make it work. Is there any preference for Uproot and Awkward compared to our data frame, which is the preferred one, in which case? We lost it there. Yeah. No, actually. Both have their advantages and disadvantages. Our data frame is part of Root and it has great integration. It does not suffer from the slow for loop problem that PyRoot does because our data frame doesn't have you write a for loop. It's a functional interface where you pass in a function and it'll run that function. And that function, even when you're in Python, that function can be a string containing a C++ function, and then it compiles and runs at C++ speeds, just like the Numba examples that I gave at the end of my presentation. So they both have their advantages. Jim showed e.g. getting an array of the first 20 events. What happens if an event has no element in it? Actually, I had an example of that too. And the reason that I showed this example with just the first 20 is because I knew that further on, there were some rare events with no element in it. What happens, if you don't remember, is you get this error. In fact, it's exactly what you're asking for right there. All the events get the 0th, and attempting to get 0 index out of range because it isn't there. And then the way one way to circumvent that is don't do all events, but just the events that have at least 1, and then you can do it. Or if you want to get the next one after that, we can select even fewer events. Events that have only 5 muons or 6, I guess. There's not very many like that, but this will guarantee that the second dimension will pass. So that's how it works. And also you might want to consider masking, which I didn't really discuss. But by doing masking, instead of reducing the size of your array, oh, that's interesting. Didn't realize that was going to be slow. That's very, very interesting. Oh. Okay, something to look into. Oh.
Acta num needs an axis.
Huh? What was that?
The num needs an axis, I think.
No, I think the default is axis is 1. Otherwise the cut wouldn't work. Okay, that's something to look into. Both the fact that that was slow is a clue that something was going wrong, and then of course there was an error. So I'll look into that. All right, arrays has a convenient cuts keyword while .array does not. Is that on purpose? Yes, because .array will give you just that array. So it's not computing any formulas, and therefore it can't cut anything. The arrays method plural can give you multiple things, and well, cutting on some other branch means that you're getting more than one branch. So yeah, that's why. Let's see, can we run any NumPy-based function under numba.jit? The answer to that is no. Numba supported NumPy. Numba keeps a list of all of the supported Python features and the supported NumPy features, because when Numba looks at that Python code, it gets rid of the Python. You know, it takes that and uses that as a guide for some LLVM that is going to create and compile. That means that absolutely everything that exists that could be run there has to have a specialized reimplementation in LLVM. So many NumPy features have been reimplemented for use in Numba. Awkward arrays have a reimplementation for use in Numba, but not everything is going to work. And so because of that, the recommended procedure for that is to only run numba.jit on small functions that need to be sped up. Like you've got your analysis, you're doing all of these things and you're using all sorts of different kinds of Python objects, but then one part of it is slow because you're running over 1 billion events and you're doing something complicated. That function is the thing that you want to just-in-time compile. And if you make any kind of error, let me, I bet it would be an error if in this function, which does some for loops and it returns a muon object, if we also return an integer, I bet that's going to be an error. So no problem when you first define the function because it doesn't compile it until you pass in an argument. Pass in an argument, and this is what a Numba error looks like. Let's scroll. Somewhere here, it's telling us that this return is no good, because whereas this would be a perfectly fine Python function, and here it's going to run slow because it was not compiled. That's a perfectly fine Python function because Python doesn't, is loose about types. If something gets compiled, it's not loose about types. It has to know those types up front, and it won't statically compile. None is allowed because that's an option type. The return type of this is a muon or none. So yeah, Numba is limited.
Oh, so Numba can't deal with union types beyond whatever the type is plus 9?
I have not seen Numba successfully creating unions.
Okay.
And actually, because of that, the union array in Awkward is the one thing in Awkward that's not implemented in Numba because of the troubles with unions. A union is a type representing more than one type. So yeah, and so because of that, you might find it better to essentially just-in-time compile in our data frame instead of Numba. But try both. Whatever works best for you. Can we use uproot instead of using root at all? Or there's some cases where root is superior than uproot or pyroot. Well, there's not or pyroot because pyroot is root. So if you're using pyroot, you're getting the full power of root. Just don't do it inside of a for loop over a million events. So are there cases where root is superior? Yes. As I said about file writing, we have some basic ability in Uproot 3 for writing files, histograms, and really basic TTrees. But if you want to write something complex, or if you want to write fast because you're doing a lot of it, a lot of writing, you should use root. Certainly, nobody's going to be tossing out root. Certainly not the collaboration frameworks for making all of the data in the first place. Naturally, no. Uproot exists for convenience of doing certain types of operations, especially for the end user data analysis. Like, you're working on some limited resources inside of your university. You're familiar with Python. Using things with the Python ecosystem is just second nature to you. Then these are all reasons for using Uproot, because Uproot meshes well with both the scientific Python ecosystem, particularly the fact that you can pip install it, and also it's a fairly significant subset of root. It's particularly the things you can use in analysis. Are the cut strings parsed as C++ code? No, they are parsed as Python. And any names that you see in those cut strings are names of branches, which can include dots, by the way. And this is really the main difference between if you're doing just-in-time compilation in our data frame with root and pyroot versus using uproot. You're passing in the Python strings, or using Numba. Again, it's Python. That's really the main split here. Can we run any NumPy-based function under, oh, I answered that one. Using events, TTree arrays, awkward, zip. Can you deal with different numbers of muons, electrons in the same event? Yes, yes you can. And that actually, this is an advantage of using awkward array over pandas. So that, again, they have their pluses and minuses. Pandas is great for a lot of things, but particularly like pivot tables and joining, if you're familiar with SQL like joins. The thing where pandas doesn't do so well and awkward array is useful is if you have data with a different number of muons as electrons and a different number of jets, awkward array can make an array object with different numbers of each of these things. I just didn't happen to have any sample files that illustrated those. Why do we have awkward arrays? Can we just open using normal arrays? What's the difference between jagged, awkward, and normal arrays? So we have awkward arrays because NumPy arrays of NumPy arrays the thing that I showed. Let me scroll up to it. Here, this. Here, muon PT, there's 0 or more muons in each event. So if you do this in NumPy, then you'll get array, which is a Python NumPy object, of arrays, which are Python NumPy objects. And having a million of these little tiny NumPy arrays is, first of all, not efficient, not a great use of memory, and it's slow to create and loop over all of these Python objects. And also, you can't express things like, I want to select all the events and take the 0th in each event. Because as far as NumPy is concerned, the things in these arrays are opaque. It doesn't know what these objects are, even though they happen to be NumPy arrays. And is not able to think of this NumPy object array of arrays as a multidimensional thing. Whereas awkward arrays, it's seamless. It's able to think of the variable length nested structures as a multidimensional thing. So that's why we have it. It just couldn't be done any other way. And what's the difference between jagged and awkward? Awkward is just a more general word than jagged. Jagged is specifically this case where you have like these data here, different numbers of numbers in each event. And then to say that and then the awkward array library is a library that handles jagged arrays, but also other data types like records. And remember, I did the masking with none. So missing values. I mentioned union array. You can have 2 different types. You can make an array of electrons and muons. And the electron type can be different from the muon type. You can't pass that into Numba, but you can make it, and you can do some calculations on it. So that's why we have this awkward library. And actually, for more on that, we can get into the ultra meta talk within a talk. There I am, smiling. And there I'm actually, in that talk, trying to justify the existence of awkward array to the people who make NumPy and Pandas and the various tools. So yes, there is a reason for it. Are the TTree array alias formulas the same as T formulas? Not exactly. Some other syntax, yeah, they're Python syntax. So T formulas, like in TTree draw, it has a different syntax. And so Uproot 4 was made with a pluggable system for different syntaxes to use in that cut thing. The one plugin that is implemented is Python, because Python is readily available when you're in Python. But the idea is to extend that and also make a plugin for T-formula using, say, there's a scikit-hep project called the Formulate package,
Jim, if I
which
can
handles.
interject on that real
Sure.
quick. So in fact,
Okay.
Either Jordan or Lucas already made a drop-in replacement for TTree draw or T-formula using Formulate plus awkward 0. So
Awkward 0.
yeah. But
Yes.
so it needs to be
Right.
done for awkward 1, but it's something like this where you have this drop-in replacement is already out there. Just not widely
Excellent.
advertised.
Yes.
I think.
Yes. Well, thanks for advertising it. Yeah, I'm glad that's there. And specifically, that question was not about awkward. It was about Uproot, because Uproot has the arrays where you can put in a formula.
Oh, right, yeah.
And that's where we want to do that. Yeah, right.
If I can jump in as well, it's interesting, Lindsay. It's good to hear there's a version out there, because we've been using another version that we've written in the past.
Okay. Yeah. Right.
that I spoke with Jim a while about trying to move it into something more official. But it'd be good to see if we've converged on a similar version.
Right.
Yes, we need to agree on things. I agree on that.
Right. Right. And then we show the XKCD about the formula, about the 14 standards. Right.
Yes.
Yep. So I would definitely want to answer this question. Is iterating over arrays fast in Python? I thought Python is very slow when it uses loops. Yes. And that's what most of this is for. Python is very slow if you write a for loop and it's not in a Numba compiled function. If you're using NumPy's syntax, like you put square brackets in order to select events or select particles, that kind of selection where you don't actually write the word for is fast. That goes to compiled code. And so there's no problem with the performance there. Same thing if it's awkward array, you put for brackets, and that goes into compiled code. And yeah, that's, in my mind, fast is not a number, it's a Boolean. Are you in Python speeds or are you in compiled speeds? So, so yeah, using the array at a time interfaces, like you pass an entire array to the square root function to get the square roots of all the numbers in the array. That is in the fast category. That goes to compiled code. Now you can write, that's the reason that Numba is exciting, is because now you can also write for loops if they're in this kind of, if they're in the decorated Numba function, and Numba is able to determine all the types of everything and therefore compile it. Then even those for loops, those Python for loops can be fast too. How do you convert root file to NumPy array if your n tuple has different length of branching? So the kind of n tuple I think you're talking about here, because you say, for example, PT of tracks in each vertex, which is varied, you are describing a jagged array. Yana, this is technically speaking, the length of those arrays are all the same. If it's in a TTree, each of those branches in all the examples I've ever seen have the same number of entries. So the lengths are the same, but then the length in the second dimension is what varies. And that is a jagged array.
Yes.
As you iterate.
This was a question because, sorry, I faced this problem not using Uproot but PyRoot. I couldn't convert to the NumPy when you have another dimension in the branching when you store in the two-dimensional vector, and another dimension is not is changing.
Right. So then that's why we got started on all this. Actually, that's why jagged array was introduced in Uproot 2, maybe 1. And then it was split off into a whole library of awkward array to deal with all of these awkward arrays. When you're iterating, can you control the size of the chunk? Yes, you can control the size. I think it's called step size. So if I can find .iterate this example here, I think I can say step size equals, make it a number of events. Actually, I happen to know that this is small. Number of events, yeah, there. So smaller step size means there's more steps. Or you can make it a size, which kilobyte each is a very small size. I'm making small because I know this happens to be a small example. I believe the default is 100 megabytes or single files. And yeah, so you can control that. And this size, if you give it a memory size, is the size of all the arrays that you're reading in. So that's really a question of how much do you want to read in each step. And actually, we should be getting on to the next talks. But until Eduardo stops me, I'm going to keep answering questions. How hard is it to write code that's as performant as Uproot from C++ and Root? Is someone who is proficient at C++ and Root at a disadvantage? If you're proficient at C++ and Root, you are not at a disadvantage. If you're proficient at C++ and Root, you can really optimize the performance. There's no question about that. The reason that these exist is because people like using Python. They want to write simple things to concentrate on the analysis. But certainly if you have great C++ skills and a lot of knowledge about Root, I'm sure you could write something that is as fast or faster. Do you need to manually clear the cache, or does it vacate itself? It vacates itself. It's an LRU cache that means least recently used. So as new things are read, if it needs more space, it'll drop the things you've least recently used. I've answered that. Is it possible to create a hierarchy of directories with histograms inside? By create, I think you mean file writing. I forgot to mention that this is another limitation in Uproot's file writing, that it can only make one directory. So again, Uproot's file writing is really just for very simple files. However, if you're reading, you can definitely read a hierarchy of directories. So it's really asymmetric about the read capabilities and the write capabilities. If one needs to incorporate methods where multiple data frames need to be loaded in memory to make histograms, what is the optimal way to do this? The optimal way to read multiple data frames and arrays? Well, okay. Optimal way to read multiple data frames is to have multiple arrays calls. And in particular, you probably want to have multiple data frames if you're working with data that have different number of elements per event. So for instance, if you want muons and jets, there's a different number of muons in each event than there are jets. And Pandas data frame can have only one multi-index because it can have only one index. So you really should have a different data frame for your muons than you have for your jets. So you already have two different data frames, and then you want to do joins of those data frames to work with both the muons and the jets. And the appropriate way to do that is to call uproot.arrays, I'm sorry, TTree.arrays for just the muons, library equals pandas, TTree arrays for just the jets, library equals pandas to get your two data frames. Or if they're awkward arrays, you can load them both together. And there's, yeah, you want to clarify?
Yeah, Jim, just say it's going to get to 2:45. Shall we then?
Yeah.
Sum the.
Absolutely. Like I said, I was waiting for you to stop me.
You actually went through an impressive number of questions, which is good because that means that people indeed had the really following and had a bunch of questions, which is normal, you know, if you haven't seen this before. But I see from